Hi, I'm Nathan Nesbitt, and I'm going to do a little segment for you about conservation of angular momentum. So, if you think about something spinning, like a point mass spinning about a point, you have a point and then you have your point mass. As it moves, it's going to trace a circle, right? Okay, so there's momentum associated with this. Momentum is just an idea of how much energy there is in something moving. So if we want to specify how fast this is going, for a car you have something that's translating linearly, and we call this velocity v. So a car can be going 5 miles an hour. So if we're talking about how fast something's going around, we can say right now this is going 5 miles an hour up, but then over here we have 5 miles an hour sideways. We can talk about how fast it's spinning by talking about the angular velocity omega. So that's how much time it takes for it to do a complete circle. And that doesn't depend on if you're in here or if you're in here. It's just your angular velocity. So if we call this distance r, then the velocity here, which is v equals r times omega. And if we have momentum, which is mass times velocity, v equals r omega, we can talk about angular momentum for a point mass, which is mass times r times omega. So there's this idea that angular momentum is conserved. So if I'm spinning freely and there's no forces on me, angular momentum isn't going to change. But I could change the radius of this point mass if I wanted to. And in that case, I'd use the equation L1 equals L2. Or I'm not going to change my mass, but I want to change what r is. And consequently, omega is going to change. I'm going to have r1 omega 1 equals m r2 omega 2. Or my omega 2 is going to be r1 omega 1 over r2. So this is the radius that I start out with, this is the radius that I end with. If my radius that I end with is half what my radius that I started with, then my ending velocity is going to be double what my initial angular velocity was. So I'm going to try and show this to you with myself. Okay, so I have a turning table and two masses. So if I start out spinning on this with the masses far out, I can make r smaller and my angular velocity increases. If I make r large, my angular velocity decreases. However, throughout this process, my angular momentum is staying the same. This is conservation of angular momentum. This is what ballet and ice skaters do to make themselves spin fast. So that is conservation of angular momentum. I hope you were able to follow it, and have a good day.